Hello friends, uh, welcome back to my YouTube channel. I hope you all are fine. I hope that you are watching my videos. Today I'll be discussing storage vessels. I will continue my discussion on storage vessels. This will be part 6 of my discussion. For those of you who have not yet seen my earlier videos on storage vessels, I am giving links to those videos in the description section. So in part number 6 of storage vessel, I'll be continuing my discussion on design of storage vessels, and this time I'll be talking about how to design a self-supporting conical roof. In part 5, I have discussed how to design shell for a vertical cylindrical tank, vertical cylindrical storage vessel. Let me tell you, I have been discussing design for a vertical cylindrical storage vessel. So today I'll be discussing how to design a self-supporting conical roof for such a storage vessel. So let me start my discussion. A self-supporting roof that we are talking about, it may have different shapes. So it could be a conical roof like this, and we are going to discuss design of that, or it could be a dome roof like this, or it could be an umbrella roof, umbrella shaped roof. So in my discussion I'll be concentrating on designing a conical roof, a self-supporting conical roof. So the task is to design a self-supporting conical roof. You please read this as roof, a self-supporting conical roof for a vertical cylindrical storage tank. Okay, now a self-supporting roof, self-supporting conical roof, it must be designed to support superimposed loads. First thing, superimposed load, let us denote it as SL, superimposed loads. And then it must it must also support, it must also withstand, the self-supporting roof must also withstand load due to internal pressure. So, and I'm denoting it as IP. Now what are these superimposed loads? Let us understand. Yes, these superimposed loads, they act on the horizontal plane. So you have a horizontal plane, and the superimposed loads will be acting on the horizontal plane. These are in addition to dead weights of the roof and its supporting structure. So in addition to the dead weights of the roof and its supporting structure, we need to consider the superimposed loads which are acting on a horizontal plane. What are the examples of superimposed load? It could be wind load, weight of the personnel walking on the roof. So sometimes due to one or other reason, uh, personnel may be going onto the roof, they may be walking on the roof, so you also have to consider that. Then weight of snow, if the storage vessel is to be used in places where there is frequent snowfall, then you also have to consider weight of the snow. So these are just examples. You have to take care of these superimposed loads. And for design purpose, a minimum of 125 kg per meter square, it is considered for design. For designing a self-supporting conical roof, we consider a weight minimum load of 125 kg per meter square. It could be more than that, but at least you have to consider 125 kg per meter square. You can use a lesser value in the case where snowfall is very rare. If uh, there is no snowfall, or even if it is rare, then you can use a lesser value for the superimposed load. It could be less than 125 kg per meter square. Okay, then load due to internal pressure, I have talked about it. So it has to be considered differently for different categories of tanks. So for example, for non-pressure tanks, it is taken as 75 kg per meter square, and for class A tanks, it is taken as 200 kg per meter square. For class B tanks, it is taken as 550 kg per meter square for internal pressure. And in case of vacuum, so for non-pressure tank, it would be 25 mm of uh, 25 mm of water gauge, and this will be for class A tanks, it will be 65 mm of water gauge, and even for class B vessel, it would be 65 mm of water gauge vacuum. If vacuum has to be considered for design, then this will be the values. Okay, so load due to internal pressure is considered in this way. For non-pressure tanks, it is 75 kg per meter square. For class A tanks, it is taken as 200 kg per meter square. For class B tanks, it is taken as 550 kg per meter square. So total load for the design will then be the superimposed load plus internal pressure. Total load, let me denote it as PT. It will be the addition of superimposed load plus internal pressure. Superimposed load we have just seen. I have just talked about it, and then the internal pressure will be taken according to the category of the vessel. So this load will be having units of pressure, Newton per meter square, or kg per meter square, or kg per centimeter square. Okay, so you are going to design a self-supporting conical roof so that it will support, or it will withstand superimposed load, and it will also withstand load due to internal pressure. Superimposed, as far as superimposed load is concerned, a minimum of 125 kg per meter square has to be taken. You can use a lesser value uh, depending on the conditions, and the other component in total load is internal pressure, and internal pressure will depend on the category of the tank that you are going to design. Okay, next, so whatever you have the total load that we just understood, PT, this total load is going to induce stress in the conical roof, and this stress is given by this equation. The stress induced in the conical roof due to the total load is given by this equation. It is F is equal to PT into DH divided by 2 into TH into sine theta. What are the terms involved? PT, as you know, this is the total load on the roof. DH is diameter of the conical roof. TH is thickness of the conical roof. And theta is angle between the conical roof and the horizontal. So I'll show that. So you have the conical roof, schematic representation of the conical roof. This is the vertical, and we are talking about this angle. So this angle is this angle is made by the conical roof with the horizontal, and that will be theta. Whereas diameter of the conical roof is this one. So this is the diameter of the conical roof, DH. Okay. Now this stress that will be induced, it is compressive in nature. It is a compressive stress. So what is the significance of this stress? If this stress reaches a critical value, if the stress calculated by this equation, if F it reaches a critical value, what is going to happen? There is a strong possibility of failure of the roof plates, failure of the roof plates due to wrinkling. So once this stress reaches a critical value, failure of the roof is going to occur, and that failure will be by wrinkling. Okay? So the stress that is induced due to total load is sum of superimposed load and load due to internal pressure. This stress is compressive in nature. It can reach a critical value, and if it reaches a critical value, there is a strong possibility of failure of the roof plates due to wrinkling. So you have to take care of this. Okay. Again, continuing with the discussion, I'm taking the previous diagram. Now you also have an equation which will allow you to calculate the critical value. We don't want the stress induced in the roof to reach the critical value. What is this critical value? The critical value for the compressive stress is Fc is equal to E upon under root of 3 into 1 minus mu square into Th upon R. What are the terms involved in this equation? E, capital E, is modulus of elasticity for the material, and we are talking about mild steel. Then mu is Poisson ratio, it will be 0.33. Th is the thickness of the conical roof. R is radius of curvature of the roof, and you can calculate it from radius of the roof. The radius, I'm telling you how to do that. The radius of curvature is given as R is equal to RH upon sine theta. What is RH? RH is radius of the conical roof. That means RH is given by this equation. It will be half of the diameter. So RH is equal to dH upon 2. Okay. So for the conical roof, will critical value of the stress will be given by this equation. On previously we had written equation for F. We don't want F to go beyond this critical value. So critical value is given by this equation. You can read the equation. Various terms involved in the equation I have written over here, and each and every term now you can use in this equation and get an equation that can be useful to us. Okay, let us continue with this. So from the previous slide, I will continue with this equation. We had written equation for critical stress. Fc is equal to E upon under root of 3 into 1 minus mu square into Th upon R. Now what we will do, we will use equation for R, radius of curvature. Radius of curvature is radius of the conical roof divided by sine theta. So if I use that, equation for critical stress will be Fc is equal to E upon under root of 3 into 1 minus mu square into Th upon Rh upon sine theta. So in place of R, we have used this equation. Further, if you simplify this, it will be Fc is equal to E upon under root of 3 into 1 minus mu square into Th sine theta. I have just rearranged the terms. Th sine theta divided by Rh. Next, Rh, now we will express it in terms of diameter of the conical roof. So Rh is dH upon 2. So if you use that in this equation for Fc, this will be Fc is equal to E upon under root of 3 into 1 minus mu square into Th sine theta. Now in place of Rh, it will be dH upon 2. And after simplification, you'll be having this equation. Fc is equal to E upon under root of 3 into 1 minus mu square into 2h sine theta divided by dh. So this 2 goes in the numerator, and you have this equation. Okay. Now let us continue with that. From the previous slide, I will take the equation that was obtained. The equation is Fc is equal to E upon under root of 3 into 1 minus mu square into 2 into Th into sine theta divided by dh. Now the permissible stress is taken with a factor of safety of 12. So the permissible stress we are going to get from the critical stress, and it will be taken by considering a factor of safety of 12. That means permissible stress will be critical stress divided by 12. So permissible stress, let us call it as Fp, will be Fc upon 12. And if you use the equation for Fc, Fp will be equal to 1 upon 12 into E upon under root of 3 into 1 minus mu square into 2 Th sin theta divided by dH. If you simplify this, you will have Fp is equal to 1 by 12 E upon under root of 3 into 1 minus mu square into 2 Th sin theta upon dH. So we will simplify this. Now how it is done? So this 2 ones are 2 and 2 6 are 12. So I have done that. Therefore the permissible stress will be 1 upon 6 into E upon under root of 3 into 1 minus mu square into Th sin theta upon dH. If you simplify this further, it will be 1 upon Fp is equal to 1 upon 6 into square root of 3. So square root of 3 I have taken out, into E upon under root of 1 minus mu square into Th sin theta upon dH. So if you simplify this further, you'll be getting Fp is equal to 0.96 into E upon under root of 1 minus mu square Th sin theta upon dH. Okay, so you get this equation. So if you move further, you have this equation. Previously we got this equation. Fp is equal to 0.096 into E upon under root of 1 minus mu square Th sin theta upon dH. Now the stress induced in the conical roof, which we had written earlier equation for F. This is F is equal to Pt dH upon 2 Th sin theta. The stress that was induced, or the stress that is induced due to total load Pt. Now what is our job? We are going to equate the stress induced with permissible stress. That is, we are going to carry out this task. F is equal to Fp. So if you put values for the two stresses, you have this equation: Pt dH by 2 T into Th into sin theta, that is equal to 0.096 into E upon under root of 1 minus mu square into Th sin theta upon dH. So you can simplify it further, continuing with the equation that we obtained previously. Pt into dH divided by 2 into Th into sin theta, that is equal to 0.096 into E upon under root of 1 minus mu square into Th into sin theta divided by dH. So we are going to get equation for sin theta. Let us get equation for sin theta. So accordingly, after rearrangement, you get this equation. Therefore sin square theta will be Pt into dH square into under root of 1 minus mu square divided by 2 into 0.096 into E into Th square. So this is what we get after you are doing it. Okay? After you simplify, you can check for yourself. Then after simplifying it further, you get sin square theta is equal to Pt into dH square into under root of 1 minus mu square divided by 0.192 into E into Th square. And if you want to write equation for sin theta, you need to take square root on both the sides. So that will give us this equation: sin theta is equal to square root of Pt into dH square into under root of 1 minus mu square divided by 0.192 into E into Th square. We will simplify it further. Therefore sin theta will be 2.28 after simplification into dH upon Th into Pt upon E raised to 1 by 2 into 1 minus mu square raised to 1 by 4. For mile still is 0.33, so you can put that value and you can simplify it further. So you get equation. We have obtained equation for sin theta. I'm rewriting that equation. Sine theta is under root of pt dh square into square root of 1 minus mu square divided by 0.192 into e into th square. So we had got this equation last time. So what is the significance of this equation? This equation you have to, well, it can be used to calculate theta, and from theta you can calculate slope. And what is the significance of the slope for the conical roof? The slope of the conical roof, it is limited to 1 in 5 or 1 in 6. That means tan theta should be less than 1 divided by 5, or tan theta should be less than 1 upon 6. So slope of the conical roof is designed so that its slope is less than 1.5 or it is less than 1.6. The thickness of the roof is calculated to satisfy this condition. So you are going to select only that thickness which will satisfy these conditions. Okay. Again, continuing with our discussion, we had got this. Now we will rearrange the equation in a different form. We will write equation for th. So you had this equation for sine theta. Now this equation is rearranged to get an equation for th. So th is this equation. So if theta is known to you, you can calculate thickness by using this equation. The minimum thickness for the self-supporting roof is 5 mm. It cannot be less than 5 mm. And maximum thickness for the self-supporting conical roof will be 12 mm. It cannot be greater than 12 mm. Okay. So in this way, I have discussed how to design a self-supporting conical roof for a vertical cylindrical storage tank. So slope of the conical roof is important. Slope, it has to be less than 1.1 upon 5 or 1 upon 6. And the minimum thickness that you can give for a self-supporting conical roof is 5 mm, and maximum will be 12 mm. So you have to keep these things in mind before you design a conical roof for a self-supporting conical roof for a vertical cylindrical storage tank. So with this, I end my discussion on design of self-supporting conical roof. Thank you for being with me. Thanks for watching my video. Do subscribe to my channel. In my next video, I'll be discussing how to design a column supported conical roof for a vertical cylindrical tank. Please do subscribe to my channel. You please watch my earlier videos. Links are there in the description section. For now, have a nice day. Bye bye. Take care.